Any charged particle moving at a certain speed generates a magnetic field as well as a varying electric field according to Maxwell's equations. When an electric field is applied to a conductor, free electrons begin to move, and this movement results in the formation of a magnetic field around the conductor. If this conductor is wound into a circular shape to form a coil, the resulting magnetic field is uniformly distributed inside the coil. Here, Bt represents the magnetic field strength. Mu0 is the permeability of free space. Mu-R is the relative permeability of the material. N is the number of turns in the coil. It is the time-dependent current, and L is the length of the coil. Induction heating is a method that generates heat by creating electrical currents within a metal, based on the principle of electromagnetic induction. This method is highly efficient and fast since it directly converts energy into heat within the metal. To understand the physical processes behind induction heating, it is important to examine fundamental concepts such as electromagnetic induction, eddy currents, Foucault currents, magnetic hysteresis, and Joule heating. When an alternating current, AC, passes through a coil, it creates a constantly changing magnetic field around it. This changing magnetic field penetrates a nearby metal object and induces electric currents within the metal. This phenomenon is based on Faraday's law of induction. According to Faraday's law, a time-varying magnetic field around a conductor induces an electromotive force, voltage, within that conductor. This voltage generates electric currents circulating in closed loops within the metal known as eddy currents. Eddy currents encounter resistance within the metal, leading to energy loss. According to Joule's law, this energy loss is converted into heat. Joule's law states that the electrical current passing through a conductor generates heat due to the conductor's resistance. The amount of heat produced in this process depends on the current's intensity and the metal's resistance. This heat generated inside the metal ensures rapid and uniform heating. If the heated metal is a ferromagnetic material, such as iron or nickel, another mechanism comes into play: magnetic hysteresis. In ferromagnetic materials, the changing magnetic field causes the magnetic dipoles inside the metal to constantly realign. During this realignment, energy loss occurs, which is converted into heat. Magnetic hysteresis losses depend on the frequency of the changing magnetic field and the magnetic flux density. However, this effect ceases when the metal exceeds its Curie temperature, as ferromagnetic materials lose their magnetic properties above this temperature. One of the most significant advantages of induction heating is that heat is generated directly within the metal. In conventional heating methods, energy losses occur as heat is transferred from a source to the metal. However, induction heating is much more efficient as it converts energy directly within the metal. Additionally, this method is safe since it doesn't involve open flames and is environmentally friendly. Induction cooktops heat pots directly by generating eddy currents with magnetic fields, making the process faster and more efficient than traditional stoves. Since the cooktop surface doesn't heat up directly, the risk of burns is reduced, ensuring safer use. In industry, induction heating is used to melt metal blocks or scrap by placing them inside large coils. This method is cleaner, more efficient, and offers better control compared to traditional fuel-based furnaces. In steel production, induction furnaces save energy and ensure more uniform heating. Induction heating produces heat by generating electric currents within metals through magnetic field variations. Based on physical principles such as electromagnetic induction, Joule heating, and magnetic hysteresis, this technology holds a significant place in modern engineering and physics.